Equivalence classes. Let's study equivalence relations further. We have seen an equivalence relation on A can break A into subsets. Let's make a formal definition. Definition: that A be a non-empty set and wiggle an equivalence relation on A. For each A in A, class A is the set of all elements in A such that X is related to A, is called the equivalence class of A with respect to wiggle, or the wiggle equivalence class of A. In real application, when the equivalence relation is specified, then we will use the name of the real equivalence relation instead of wiggle. And we also will put the real name here if it's clear. And for convenience, we'll also simply say this is a class of A as well. It is also clear that a class A is not empty because A is always in this set. Because we talk about a equivalence relation and A is equivalent to A, therefore A is always in the set. Therefore, this set is not empty. Now let's look at an example. Example 1. Given f of n equals sine n pi over 2, n is a natural number. Define a relation wiggle on the natural number set by for each m and n in the natural number set, m is related to n if f of m equals f of n. Prove that the relation is an equivalence relation, then find the equivalence classes of the relation. So first, to prove it is a equivalence relation, and we need to verify three things. First, verify it is reflexive. In other words, we need to verify m is related to m. But this is clear because that f of m is always equal to f of m, right? Because these are functions. We talk about functions. So, and the values f of m equals f of m. Therefore, by definition, m is related to m. Okay, so that is reflexive. Transitive, we need to verify that if m is related to n, n is related to, say, p, then we need to conclude that m is also related to p. That's what we mean by transitive. Well, when m is related to n, that means f of m equals f of n. And then when n is related to p, that means f of n equals f of p, according to our definition here. So now, by equality, we have f of m equals f of p. This means m is related to p. So we have transitive. Symmetric, we need to verify when m is related to n, then we need to verify n is related to m. This is also obvious because when m is related to n, then f of m equals f of n. And by equality, you can flip. So f of n equals f of m, which means n is related to m. So therefore, it is also symmetric. Then this relation is an equivalence relation. Now let's look at equivalence classes. So to find out equivalence classes and the definition that m is related to n if the values are the same. So therefore, to find the equivalence classes, we need to evaluate the function. For first, and let's look at equivalence class of 1. So this one means we need to find all natural numbers such that f of m equals f of 1. So you need to calculate f of 1, and then you need to calculate f of 2, f of 3, f of 4, and so on. So now let's look at f of 1. F of 1, and the function is f of n equals sine n pi. So you put, for f of 1, you put 1 here. Next, f of 2, you will put 2 here, okay? So then this will be f of 1 pi. Sine pi over 2, you know it is equal to 1. And then let's look at f of 2. That means sine 2 pi over 2. That is reduced to sine pi. And remember, sine pi equals 0. And then let's look at f of 3. That will be sine 3 pi over 2. Remember, sine 3 pi over 2 is -1. F of 4, that means sine 4 pi over 2. And cancel 4 with 2, you get sine 2 pi. And remember, sine 2 pi is 0, right? By the way, if you forget, you can check calculator to do this calculation, but it is good to remember these special values. F of 5, that's sine 5 pi over 2, and you calculate 5 pi over 2, it's equivalent to, because 5 pi over 2 can be written as pi over 2 plus 2 pi, and sine is a periodic function with period to pi, so therefore this is reduced to sine pi over 2, that equals 1. And then sine f of 6, sine 6 pi over 2, that becomes sine 3 pi, and sine 3 pi is 0. F of 7, that will be sine 7 pi over 2, and that will become -1. F of 8, sine 8 pi over 2. 8 cancel with 2, you get 4, so you get sine 4 pi, that is 0. And let's look at f of 9. Sine 9 pi over 2, and this can be written as sine pi over 2 plus 4 pi, and then by the periodicity, so you reduce to sine pi over 2, you get 1. And then f of 10, and that will be sine 10 pi over 2. 10 cancel with 2, you get 5 pi, and sine 5 pi is 0. And you can continue this one. And now you probably have seen the pattern. So sine 11 pi over 2 is -1, and f of 12, sine 12 pi over 2, 12 divided by 2 equals 6, sine 6 pi is 0. So now you have seen the pattern, 1, 0, -1, 0, then 1, 0, -1, 0, 1, 0, -1, 0. So this helps us to get the equivalence class. So equivalence class of 1, that will be all the numbers that when you evaluate, you get the same value. So f of 1, you get 1, and then f of 5, you get 1, and then f of 9, you get 1. Therefore, this set will be 1, 5, 9, and then this pattern increased by 4. So next will be 13, 17, and this is the equivalence class of 1. For equivalence class of 2, then 2, you look at f of 2, it's 0. So that f4, it is also 0. And then f of 8, it is also 0. f10, f12. So you see that all even numbers, the value is 0. So 2, 4, 6, 8, 10, and so on. And then let's look at class of 3. So class of 3, and the value is -1. So you have 7 is -1, and f of 11 is -1. So this will be 3, 7, 11, increased by 4. So next one would be 15, 19. So these are the 3 classes we have, and we do not have any other classes because the value we have is 1, 0, -1. So, and then all these three classes together, you can see, and that the union is equal to the natural number set, right? So these are all even numbers, and then 1, 3, 5, 7, 9, 11, these together is all odd number set, so together. But mutually, they are disjoint. So 1 and 2, the union intersection is empty. 1 and 3, the intersection is empty. 2 and 3, the intersection, it is also empty. So this together is a partition of the natural numbers set. Let's look at another example. Example 2. Define a relation wiggle on the plane r squared by xy is related to uv if x squared plus y squared equals u squared plus v squared. Prove that this relation is an equivalence relation, then give a geometric description of an equivalence class. This example is in a book, so you can also read the book. To prove this is a equivalence relation, we need to do three things. First, to verify it is reflexive. In other words, we need to verify xy is related to xy. But this is simple because x squared plus y squared, it is also equal to x squared plus y squared. Therefore, x squared plus y squared equals u squared plus v squared means xy is related to uv. We have this equality, so that means xy is related to xy. So this is reflexive. Transitive, xy is related to uv, and then uv is related to st. Then we want to show that xy is related to st. Now, xy is related to uv means x squared plus y squared equals u squared plus v squared. uv is related to st means u squared plus v squared equals s squared plus t squared. And then by equality, we have this can connect. Therefore, x squared plus y squared equals s squared plus t squared. That means xy is related to st by the definition of this relation, because if the squares are equal, then they are related. So this relation is transitive. And let's look at symmetric. xy is related to uv. We need to show uv is related to xy. By definition, xy is related to uv means x squared plus y squared equals u squared plus v squared. But equality can switch. So u squared plus v squared equals x squared plus y squared. Therefore, we have uv is related to xy. So now we verify all the three properties. Therefore, this is a equivalence relation. Now let's look at what a equivalence class look like. For that purpose, let's pick a very specific number to illustrate. For example, we pick 3, 4. This is a point in a plane. So the equivalence class of 3, 4, in terms of definition, that will be all xy such that x squared plus y squared equals 3 squared plus 4 squared. Now, you know 3 squared plus 4 squared equals 5 squared. So this, you know, it is a circle, right? X squared plus y squared equals 5 squared. This is a circle centered at 0, 0 with radius equals 5. So therefore, the description of this set is all points on the circle centered at 0, 0 with radius 5. Now we can give a general description for any point xy. So if we have any point xy, then the equivalence class will be all point uv such that uv is related to xy, or u squared plus v squared equals x squared plus y squared. So x squared, y squared are given whenever a point is given. So then u squared plus v squared is a circle centered at 0, 0 with radius equals square root x squared plus y squared, like we did for 25, and phi is the square root of 25. So the description of this equivalence class is all points on the circle centered at 0, 0 with radius r equals square root x squared plus y squared. So you can see this relation has infinite many circles. That is, each circle is a class, is a equivalence class. So all these circles is a partition of the plane. Equivalence classes form a partition, and let's summarize this as the following theorems. By the way, example 2 is in the book, so you can also read the book. Theorem 1, that we go be an equivalence relation on A. For each A, B in A is related to B if only if class A equals class B. To prove this one, because we talk about if and only if, this is the standard notation for if and only if. We need to do two parts. First part, we need to prove if A is related to B, then class A equals class B. To prove two sets are equal, we mentioned that before, we need to prove that A is a subset of B. Then we will prove B is a subset of A as well. So first, let's look at proof A is a subset of B. So for each element in A, in class A, we want to prove this element is also in B. Now, for each element in A, because this is class A, that means X is equivalent to A by definition, okay? Because it is a equivalence class. So X is equivalent to A. Now, because we are given that, A is related to B, then we have X is related to B as well, because X is related to A related to B. So then by transitive, so we have this one. So X is related to B, that means X is in class B. So now we prove that for each element in A, it is also an element in B. Therefore, A is a subset of B. The other way, we want to prove B is a subset of A. So now let's pick an element in B. That means X is related to B, because that's the equivalence class means. And now, because we are given A is related to B, then B is related to A by symmetric, because a equivalence relation is symmetric. So B is related to A. Now we have X is related to B, B is related to A, so we can get X is related to A by transitive, because an equivalence class is transitive. Equivalence of relation is transitive. So X is related to A, that means X is in the set A. That's what equivalence class definition is. So now X is in B, we get X is in A. Therefore, B is a subset of A. So A is a subset of B, B is a subset of A together. That means class A equals class B. And this is the way we prove two sets are equal. And then we also need to prove the other way for if and only if. So now if class A equals class B, then A is related to B. We need to prove this. And this part is pretty easy because when A is in set A. Now, because that is equal to set B, then A it is also in set B. But A in set B means A is related to B by the definition of this equivalence class B. So that's the proof we need. So therefore, we have done the proof of this theorem. Now let's look at next one, that we go be an equivalence relation on A, and A sub I are elements that they are mutually not Wiggle related. Then the set of all equivalence classes of A sub I form a partition of A. And that is the example just now we illustrated. For the sine function, we get three classes, and these three classes together is a partition of natural number set. And then for this relation defined by the distance or the circles, then each circle is a equivalence class, and all circles in the plane is a partition of the plane. And this one, it just said that, for each equivalence relation, and then we have elements, they are mutually not related. And these elements, each one can form a equivalence class, and all this equivalence class together is a partition of the set. So this is our discussion for this lecture. For your homework, you may do assignment number 46.